there you go. And there I go. Okay. So, one of you or two of you asked about photography. How does photography work? Well, it works out pretty well, but it fits into our unit on electrons. So, before you were born, photography used to have film, like a plastic film, that had an emulsion of silver particles on it. And what would happen is light would hit the silver particles, and those silver particles would turn dark. Does anybody have transitions lenses, the glasses that turn gray when you go outside? Okay, so if you're familiar with them, they basically work on the same process. You go outside, and then the light basically makes the glasses turn gray. That's what happened with film, old-style film. And then you'd have what's called a negative, and a negative is, just like it sounds, things that are light would be dark because there would be more light, and then things that were light would become dark because there were less light. And then those negatives, you'd have to replace the process in a dark room and shine light through the negatives to make an actual picture. So dark rooms were like, remember like the private investigator looking at the film? Oh yeah, he's guilty. So that's what they were looking at. They were looking at the negatives and they're like, oh, okay. Then they shine light through the negative onto film and you get a piece of paper that had an image on it. Okay. Nowadays, it's far more simple. Fun fact, Kodak was a big, the company that made a lot of film was Kodak, and they invented the first digital camera. Does anybody have a digital camera made by Kodak? Wow, okay.
Not the first one. They're out of business.
They're out of business now because they didn't realize the value of what they had. But nowadays, digital photography works a lot like what we've been talking about with atomic absorption and atomic emission. How it works is there's tiny little sensors, on one big sensor, and light comes in and causes an electron to jump up, and it jumps up so far that it falls off the atom. And it goes through a tiny wire and tells the sensor, light hit me right here. And then the sensor says, okay, I'm going to make that a green light, that or blue light, and that a red light. And then light comes in, hits the blue sensor, and the computer says, that's a blue dot. Light comes in, hits the green sensor, and the computer says, that's a green dot. Light comes in, hits the red sensor, that's a red dot. And then you mix those dots together with how many hits you get per a certain amount of time, and you get a color. If you get a whole bunch of hits on blue and nothing else, it's blue. If you get a whole bunch of hits on white, or so a whole bunch of hits on blue, a whole bunch of hits on green, a whole bunch of hits on red, that pixel becomes white. If there's no hits on anything, it becomes black. If there's a whole bunch of hits on red and a whole bunch of hits on green, then that just becomes yellow. If a whole bunch of hits on blue and a whole bunch of hits on green, that pixel becomes cyan or sky blue. Make sense? So that's how digital photography works. What really blows my mind is there's about 1 billion of these little sensors on a square inch, or even like a square centimeter in your digital camera. A whole lot.
You know, here and there.
I don't feel it. Want you to leave it here? Or you go to the next class? Go visit me later. So there's tons of these tiny, tiny, tiny little sensors crammed onto these little teeny blocks in your cell phone. That's what really blows me is how small we made it. So that's how digital photography works. Questions?
The more sensors, is it like higher definition?
Yeah, so when you hear about megapixels, what a megapixel is 1,000,000 pixels per square inch. So 1 megapixel is 1,000,000 pixels. Mega is 1,000,000. Remember the prefix? Mega is 1,000,000. So a 12 megapixel camera has 12 million pixels in a square inch, which is redonkulous. But yeah, so yeah, the original digital camera had it was like 64 by 64. It was like a tiny millipixel. Yeah.
How did they get all of those on that? Like I understand now they have computers and stuff that do it, but how did they do it the very first time?
What's called lithography. So imagine you're going to draw a picture with a paintbrush. Okay, your paintbrush can only be so small. So what they do is they use lithography, which is basically using a laser of some kind, sometimes ultraviolet, sometimes X-ray, to draw the sensor into a piece of silicon. And because you're talking about something itty bitty bitty, like an X-ray laser, then they can draw very, very small. They have a very small paintbrush. So that's how they basically draw it onto a piece of silicon. Beyond that, like 3rd and 4th level physical chemistry will get you there when you're junior or senior level in college. But yeah, that's how they do it. So, and then again, when they reproduce it on a monitor, you get your blue and your green and your red dot, and then you mix it together and you get pixels of various colors. You see this when you sneeze on your computer monitor. You see the little dots? Yeah. Okay, so there's that. Okay, any other questions before we move on? Then off we go. Okay, so a lot of this is going to be a review that we've already talked about. We're just going to attach some names to it. And I'm going to ask you to remember what I told you earlier this year, because apparently some teachers are saying, Mr. Byers is a crackpot. He tells you to do dumb things. I want you to write down everything you see. Well, don't write down everything you see, please. If you can't sum up what you've seen, what you've heard in your own words, you don't understand it. And you should not be writing everything you see. Please, please, please don't write everything you see. I basically make it verbose like this for the people who borrow my PowerPoints and are dumb. So moving on. So, electrons. We talked about this. When an electron gains energy, what does it do?
Jump up a little.
It jumps up. Does it stay there for very long?
No.
Nope. Immediately jumps back down, back to the ground state. So they go from a ground state to an excited state, they come back down. Now when they come back down, they give off a photon of light of various colors. This is the emissions spectrum. A spectrum is like a broad collection, if you will. So this is all of the drop downs for hydrogen. There's a red, a yellow, a green, a cyan, a blue, and there's even a violet over here. And I think there was one or two that you can't see because of the projection. You can barely even see the violet, right? It was right there. But this is the emission spectrum for hydrogen, the simplest atom there is. Hydrogen has one electron, and it has 7 or 8 drop downs that make little bands. Now, if you looked at it with the naked eye, it's going to look kind of whitish because you got some red, some yellow, some green, some blue, and they all mix up. Okay? In reality, that's what a computer would see. A computer would see all the little bands of light. That is called the emissions spectrum. When you electrify gases or electrify any atom, that's what you get. Now, that's just for hydrogen with one atom. Can you imagine what the emission spectrum would be for an atom that had 100 electrons? Each of those electrons dropping down? It's going to be huge. Now, the important thing about emission spectrum is each of these lines does not represent the same amount of energy. What lines have the most energy? What color? Yeah, blue and violet, exactly. So this might be a transition from level 7 down to level 1. Okay. This might be a transition from level 5 down to level 1. These might be the transition from level 4 down to level 2, or level 3 down to 1. And this might be the transition from level 6 down to level 5. And this might be the transition from level 2 down to level 1. Okay? So the bigger the transition is, the more bluer the light will be. And you might even have ultraviolet, where it's like a bigger transition based on a bigger atom. But in general, the more bluer you have, more violeter you have, the bigger your transition is. The more redder your light is, the lower your transition is, a small transition. Okay. Does that idea make sense?
Yeah. Yes.
Okay. So, because of this, all atoms have a quantum fingerprint. We can use this phenomenon to look at atoms that are far, far away and say, I know what that atom is. Because as light or energy goes into the atom, it starts releasing energy. I know exactly what it is based on its fingerprint. That's the area of what's called spectroscopy. Spectroscopy literally is the study of spectrums. Spectroscopy, the study of spectrums.
Wow.
Question, Devin?
No.
Okay. So, in fact, if we had really good prisms or other kind of material, we can actually say, oh, that sodium that we put in there, that sodium spray or the lithium spray, that's got these lines. The spectroscopy basically uses a computer to slow the process down and then record it and say, oh, that's lithium. Oh, that's sodium. Devin.
So is this how we know what atmospheres are on other planets?
That is exactly what we use it for, which is the next slide. So let's go ahead and talk about it now. Same question, or can I address this first? Okay, so I'll come back to you, Bailey. So Devin asked, is this how we know what the atmospheres are on other planets? That's exactly how we know what atmospheres are on other planets. So we look at starlight coming through Venus, and some of the starlight is missing certain bands. And because it's missing certain bands, we know that's the gas that is absorbing those energies. Okay? And it's not that's not emissions, it's what's called absorption spectrum. The absorption spectrum is what you get when you have white light minus things. Okay? So we know what gases are in Uranus because when light travels through Uranus, we can look at the light that comes out of Uranus.
Oh.
So if we looked at just normal starlight,
Well,
what's so funny?
because you know he's a quantum physicist, of course.
I have no idea what you're talking about. So if you teenagers and your weird sense of humor. So if you look at light, it has what's called the continuous spectrum. The entire rainbow of light, like our Pink Floyd over there, the entire rainbow of light is called the continuous spectrum. Now when starlight, which produces the continuous spectrum, travels through Uranus, some of the light, Uranus basically takes some of the light, and the light that exits Uranus allows us to see what gas is in Uranus.
Isn't it Uranus?
Yeah. I guess. It's Neptune. Neptune, I suppose. But, does that make sense?
Yeah.
So that's how we know what gases are in Uranus, because light comes out of Uranus, and we look at what gases are missing. Questions?
No.
Okay. So, Cameron.
Just Uranus or
So, is the quantum fingerprint like the general term for like all emission spectrums? Like,
Yeah. So, tantalum will have a different one than copper, and titanium will have a different one than lutetium.
the emission spectrum is the quantum.
Yep. Yeah.
Wait, Mr. Myers?
Oops. Other way. There we go. Okay. Yeah.
Okay, no. Is Uranus the only like planet that can do that?
No. All of them can. Even materials like on Mars,
Yeah.
we have a spectroscopy, a couple of really good ones. Pretty much the most advanced spectroscopy that exists is in the Curiosity rover on Mars. Because what we do is we scoop a little rock, the little Mars rover scoops a little rock, blasts it with a lot of energy, and whatever light comes back, we measure, and we send that spectrum back to Earth, and then we say, oh, yeah, there's aluminum, and iron, and titanium, and oxygen. Cool. We can use that to build a space station. Make sense?
Mm-hmm.
Oh, that's cool.
So yeah, the most advanced computer hardware is currently sitting on Mars, millions of miles away. Okay, so this is the spectrum for sodium. You remember sodium was yellow-orange when you put it in the flame?
No.
So it looked that way because there was a pretty good band at greenish yellow, a pretty good band at orange, a pretty good band at red. So mixing up together, sodium is actually yellowish. Did I answer your question?
Yeah.
Okay. But if you actually were a computer looking at sodium spectrum, you'd see there's some blues, there's some purples, there's some reds over here. There's a whole bunch of bands, but because we don't see that way, we see everything in large quantities, thank goodness, then we just see yellow.
No, I wish we just saw yellow all day. Like one day, it's just one color. The next
Sepia, you'd see everything in sepia. That's actually some photographs where that sepia is like yellowish brownish color from like old-timey photos.
Ew, like,
You know, like the Wild West.
mustard.
Yeah, that mustardy color. Because the silver compound would break down. Now, mercury, we use mercury lights to light the gymnasium and light the football field and light the tennis courts, because mercury has so many bands in the red, the green, and the blue that when you mix them together, they look kind of whitish. And for those who remember their web publishing classes, you need green, blue, and red to make white. Or the slide back there with the digital camera, red, green, and blue makes white. So mercury works really well because lots of red, lots of green, lots of blue make white. Yeah.
Okay, so since our lights are mercury, is that why like if you turn them on and then turn them off and you turn them back on really quickly, they'll all blow?
They won't necessarily all blow, but it's not good for them. And it's also why the gymnasium lights take a long time to warm up, because that mercury has to vaporize. In fact, if you look at a mercury light that's cooled down, put it in the refrigerator, it'll actually have a little bead of mercury swimming around the bottom. When the mercury light warms up, it has to vaporize that mercury. Now, mercury lights are what we've been using for the last 70 years. The problem is, one, if you break a mercury light, you have to evacuate the gymnasium because mercury vapor is toxic. So what they're currently doing is they're trying to phase them out. They're trying to use up the stock and phase them out and replace with LEDs, which are a lot better. Yeah.
So in order for the electrons to jump in energy, right?
Okay, guys, I want to hear the question, but I can't hear it because it's talking. Go ahead.
In order for the electrons to jump in energy, right?
Mm-hmm.
So like for all of these emission spectrums, is it like when the same amount of energy is applied to each atom? Like is there a constant element?
Yeah, each of these lines would require that quantum of energy to be input. So to make that green line, you would need that quantum of energy to go into the atom first. So what we usually do is just flood it with tons more than it ever needs. Like the mercury lights, we have a bunch of violets and blues that we would want to have, so we wouldn't call, so green light wouldn't come out. So we just kind of blast it with tons of more energy than it needs. But yeah, each line requires that quantum of energy to go in, so the quantum energy would come out. Okay, other questions before we move on? Moving on, okay. So we talked about absorption spectrum and the gases in Uranus. And okay, now getting to the bulk of electrons. You might have learned, in fact I hope you would have learned in previous classes, that electrons exist in shells. Additionally, remember how, was it Anthony did the standing knob on the chair? Okay, remember how Anthony could be on level 1 on the ground, level 2 on the chair, or level 3 on the table, but nowhere in between? Okay, that's the Bohr model. So the Bohr model states that electrons exist in energy shells, and we're just going to call them energy levels. Just like get to the next level in Mega Man. Okay, so energy levels, with the lowest level having the lowest amount of energy, level 1. And the highest level being having the highest amount of energy, level 7. Okay. And each a level can hold a certain amount of energy. Now we're going to talk a lot in analogy, so try to bear with me. If the analogy gets a little crazy, let me know and I'll see if I can explain it better. Devin?
Are there only 7 levels, or are you just using that?
To our level of technology, there are only 7. It's entirely possible there are more. Like there's a scene in an old Simpsons episode about 30 years or about 20 years ago where Elisa goes to the private school and it's like, their periodic table has 200 elements because it's a private school. And then Principal Skinner says, yeah, ours only has 22. And the school board's cut us back to 22 and all of them lanthanides. Doesn't make any sense, but it's a funny joke. So yeah, to our level of technology, there are 7. Now the first shell is the closest to the nucleus, and it can only hold 2 electrons. The first shell is closest to the nucleus, and it can only hold 2 electrons. It's not very big. So imagine, if you would, this analogy. Let's say we're going to all take everybody, the entire population of Boulder City High School, and we're all going to run around the track over and over again. But instead of just having the loops around the track, these loops go all the way to the middle. Till the very people on the inner side, they're going around the track like this.
Having fun.
That's all they're doing. 1 lap. 2 laps. And so on.
How long would it take to do a mile?
Now because that ring is so small, only 2 people can fit in it. Make sense? Now the next ring can hold 8 people. Yeah. The next ring can hold 8 people, and the next level can hold 8 electrons. But this ring is wider, so you can hold 8 people. So the people in that ring are moving around like this, around the outside. Kind of like they're playing musical chairs. Around they go.
And then they tackle it down in the middle.
That comes later.
Oh, that's the
So 8 people can fit in that ring. And here's the goofy thing. All the people have to have the exact same lap time. In other words, all the people have to start and finish their laps with the same amount of time.
So put the fastest kid in the back?
Exactly.
The slowest
So
kid in the
the
middle.
slowest people in the middle, they're like,
That's too fast.
It is pretty fast. And the people on the outside are like, slow down, I have to keep up with you. They're running as fast as they can. And here's the crazy
That's a
thing.
fast one.
In the next level, there are 18 people huffing and puffing, trying to keep up with the people in the middle that are only 2. But they're really moving. because they're like, oh my gosh, slow down. The guy's like, I'm going as slow as I can.
I am crawling.
Yeah. But everybody has to have the same lap time. So the electrons on the outer shells have a lot more energy. 2 in the first shell, 8 in the next shell, 18 in the next shell, and then all shells after that have 32. Again, as far as our level of technology allows us to understand.
Hold on 1 second.
So the shells go 2, 8, 18, 32. The highest energy shells are on the outside, the lowest energy shells are on the inside. All right, so what does this mean? The electrons in the lowest shell are carrying the lowest energy. The electrons in the outer shell are carrying the highest amount of energy. Now I need you to look at the wall, find the periodic table, follow the little green dot. See the little green dot?
Where is it?
Right there. Okay.
Green dot.
So this is period 1. The horizontal row at the top of the periodic table is period 1. The next is period 2, period 3, period 4, period 5, period 6, period 7. Okay. Now period 1 has only 2 elements in it, hydrogen and helium. It is not a coincidence that the first level can only hold 2 electrons.
Whoa.
Now period 2, how many elements are in period 2? 8. It's not a coincidence that the next level can hold 8 electrons.
Period 3 only has 8.
And that's where things get a little weird. Period 3 does actually only have 8 atoms, but it turns out, I'm going to explain this in a little bit, it turns out this D block electrons down here, these 10 here, should actually be up here. There's a reason that they're down here, but period 3 should actually go whoop, up, should go down and then up. So the third level does have actually 18 electrons in it. I'll explain why the periodic table looks like this in a little bit. But level 1 can hold 2 electrons. Level 2 can hold 8 electrons. Level 3 can hold 18 electrons. And all levels of that can hold 32. Okay, give me a thumbs up if you're with me so far.
I think so.
Put your hand way up like this and shake it around if you have a question. Okay, yeah, all right, good. All right, so now orbitals. Okay, question.
Sorry, so if it's set up that way, how come all the lanthanides, when they're put into the periodic table, all go into that same spot? Do they just all have the same units then? Okay.
Yeah, in fact, I drew a diagram last period of what the periodic table would look like if it was drawn properly. It would look like this,
Okay.
where you have these are the lanthanides and actinides right here, the rare earths.
Okay.
Then the metals we know of, and then the main block. The problem is we don't teach the periodic table this way because we used to use textbooks, and textbooks were limited to a certain width. Nowadays, we don't have to use textbooks. They should actually start publishing the periodic table the way it looks, because we can make it look however we want on the internet. We're not limited to a page on a piece of paper, unless you're an English teacher. So even then, but yeah, so it should be printed like that, but it's just, that's what we're limited by. Okay, so orbitals. An orbital is a shape or a path that an electron travels. And there are 4 basic types of orbitals. What is the simplest shape in the entire galaxy?
Sphere.
A circle or a sphere, precisely. The simplest shape is a sphere. Stars are spheres, planets are spheres, moons are spheres, asteroids are spheres, Uranus is a sphere. So spheres. So it should make sense that the simplest electron path would be a sphere, and it is. So the simplest electron shape is a sphere. It's called an s orbital. Maybe because it's a sphere. I don't know. It's just called an s orbital. Yeah. And the crazy thing about an orbital is it doesn't matter how you rotate it or spin it. It stays a sphere. Okay. If I rotate it over the x-axis, still a sphere. Over the y-axis, still a sphere. Over the x-axis, still a sphere. So a sphere is very simple. Now the thing about an orbital, listen very, very, very carefully. Each orbital, no matter what its shape, can hold 2 electrons. Any orbital of any level of any energy can hold 2 electrons. So the s orbital can hold 2 electrons.
No way. Wait.
Any single orbital will be able to hold 2. Okay. Now, put your fingers up like this so you understand that idea. Okay, because we're going to use it a lot. It's going to come up a lot. Okay, cool. Okay, questions so far? All right, so let's look at our green dot on the periodic table again. Here's our green dot. The H right here is in level 1. The helium over here is also in level 1. If you were to basically assign an electron to this electron would have to go into the s orbital. This electron would have to go into the s orbital. It would also fill the same orbital as the hydrogen. The helium's electron is in the same orbital as the hydrogen's electron. Okay. They're both in what's referred to as the 1s. Make sense? Now, level 2 can hold an s and the next type of orbital. Does anyone know what the next type of orbital is?
Yeah. The square
P.
orbital.
Yeah, it's P. So